In this video, we're going to explore the kW of water at temperatures other than 25 degrees Celsius. So boiling water has a pH of 6.4. Because you have extra heat and energy as you bring the liquid up above 25 degrees to higher temperatures, well, this changes the equilibrium position. Your K of equilibriums are temperature dependent. And so as water gets hotter, its pH shifts from 7 to other values. In this case, at 100 degrees, that value is 6.4. Well, the reaction is still water breaking apart. We have nothing else in solution. We're just working with pure water here. So go ahead and use this info, see if you can figure out kW at 100 degrees Celsius. Then unpause, come back, and we'll work through it. All right, if you're back, well, the whole idea of kW is that it's the equilibrium constant for the dissociation of water. So our kW is equal to the product, the H plus and the OH minus, divided by the reactant water. But since the concentration of water is constant, it factors out. And really our kW just becomes equal to the H plus times the OH minus. Well, for a pH in boiling water to be 6.4, I can find that H plus. 10 to the minus 6.4 has to equal our H plus concentration. What we'll find is that's 3.981 times 10 to the minus 7, which is more than 1 times 10 to the minus 7. That's about 4 times more. Because of the extra energy from heating up your reaction, more of the particles are able to jump over the activation barrier, the bounce point tips, and we end up with more H plus floating around than we would at 25 degrees Celsius. Well, all of our H plus in the autoionization of water comes from water breaking apart. So for every H plus that you create, one OH minus will also be created when water breaks apart. So that must also be the concentration of the OH minus. If you don't have an outside source creating either of these, then they have to be equal in amount. They come from the water breaking apart. Which means we can plug in 3.981 times 10 to the minus 7 for both of these. That must equal kW at, well, in this case, 100 degrees Celsius. What we'll find is that kW is 1.585 times 10 to the minus 13, compared to 1 times 10 to the minus 14. Our kW is larger as our temperature goes up. Well, a larger equilibrium constant means we have more on top of the division. There's no bottom in this case because it's water, which means we just have to have more products. There's more energy, there's more opportunities for water to slam into another water and break apart, creating H plus and OH minus. So our pH scale, where we consider neutral, is actually temperature dependent. This doesn't tend to come up often. We tend to do stuff at room temp. Body temp is pretty close to room temp. But technically, 37 degrees Celsius is a little bit off. The neutral point for water inside your cells is actually a little higher than it is in pure water at room temp. So your body would be a little bit more acidic looking than neutral water on the tabletop.